right, I think we can get started. Thank you everyone for attending this. I'm very honored to be invited by fellow funds, and we're also one of their portfolio company. So I'm from Dyna Robotics. My name is York, and one of the co-founder of Dyna Robotics. So our goal for building robotics is building high performance and robust generalist policies. So I'll explain more about what's the meaning. Yeah. So this, like the overall thing, you can see this on our website, what we're building. So robust foundation model that can do a lot of different tasks in a very performant way. So we're founded in last year, September, and our major goal is build general purpose manipulation robots, because basically right now there are a lot of robots that's also focusing on, for example, locomotion, other tasks, but we really think the manipulation is the very last mile for robots to actually be performant for a lot of different work streams. So that's why we focus on manipulation. And then we're a firm that we kind of combined frontier research and also commercial deployment at the same time. I know there are a lot of other companies or like big companies, research labs, that's mostly focusing on research. But for us, we really want to bring the robot to the real use case and environment so that they can leverage AI and whatever we have built out there to actually help humans to solve problems. I'm not sure if everyone is aware, but we just raised 120 million Series A round from like industry leaders like NVIDIA, Amazon, and some other big players. Yeah, so basically meaning we're also actually expanding our team, and if anyone is interested, you can contact me or directly go on our website. Yeah, so I'll explain a little bit more on this research and deployment flywheel, because this really a mixed pattern that's like not commonly seen in the industry. Because if we look back to the history, most of the like research type of company focus on research a lot, and then for deployment, it's more like if you hit some point, then the deployment gets really easy. One simple example is OpenAI, right? So for GPT model, like GPT-1 to 3 are all like kind of not very easy to deploy because there's not a lot of use cases. But when ChatGPT actually comes out, it becomes much easier to deploy. So this is like the typical pattern. But in hardware-related research company, it's becoming even harder because for software, the deployments is actually the like kind of the easy step, which is you can reach your clients, you can reach your customers just with a browser or with a phone. But for hardware companies, we really actually need to do all this distribution via like actually selling the hardware. So that's kind of like chicken egg problem. Like, should you focus more on deployment first, or should you focus more on the research problems? How we do that is we leverage research to inform our deployment or commercialization team about what things we can do right now, because everyone knows currently definitely we haven't reached AGI yet. So all the robotics companies are trying different ways to reach that. But at the same time, we also want to get the first-hand information from the clients and the industry about like what are the actual problems people want to solve, instead of just sitting in the lab and imagining what are the problems, right? A lot of like pick and place type of thing, maybe it's not important in the industry. So research is more to provide us the insight about what we can do so we can find the correct clients at this stage. And at the same time, once we have some deployment in a real environment, then it gives us a lot of like high quality data and also focus our research more on the specific areas that we're looking at. And at the same time, we also got like a lot of very cutting edge insight from the real clients about what they need. So then all this feedback gets back to the research, and so we can understand like what are the major things we need to tackle first. Yeah, so this is my co-founder, Jason. So honestly, this was his lecture, but he went to another conference, so I have to represent him here. So that's like at the beginning how we started. We use a system called Aloha. Basically, it's kind of a puppet playing system that you can control this the other two arms to perform some tasks, and then we collect the data, we send this into some neural networks, and then the neural networks can control the robot by itself by like the learned policy. Yeah, although this is a very early demo, which like didn't show any impressive things, so I think at this stage, like most people can easily do that with a lot of open source tools. Yeah. And what is the status quo for robot learning and manipulation? So currently, generalist models so far are not very reliable. So if you look at a lot of latest research, either from like Google DeepMind or any other companies, like they have very general models, but it's more for the demo purpose. So it's very hard to actually land this model directly into real production without any like human monitoring, without any like auditing. It can do the job by itself. And also there's another group of models which is really specialized. So basically they are designed for like just achieving some specific goals. But for those models, it becomes very unscalable when you want actually to scale out to different situations. That's why for like the last generation of robotics companies who are focusing on building generalist, specialist models, so far like their business is kind of getting really, really focused on narrow spaces. It's very hard to expand to like different areas with same model, with same weights. So our mission is actually we want to kind of solve this problem to make a general model that's reliable. So basically that's what I said at the beginning, which is high performance and robust general purpose robots. Yeah, so these are some requirements to achieve that. So basically for achieving do things reliably, it's very important to actually mask very complex tasks. Because if you imagine in real situation, there's no task that's very, very simple. Even like folding napkin, we showed a lot about folding napkin. To human, it's very simple, but to robots, it's very hard problem because the napkin is a soft item. It's not, it cannot be very easily simulated in any simulation environment. It can, like if you really want to make it accurate, you need to be very precise on like how to grab the napkin, how to fold it. So these are all like very small nuance that robots have to learn. And second is the generalized to on-scene environments. So a lot of robots are trained in the lab, and then when you move the robots to a different environment, for example, if you bring a robot to the stage right now, maybe it doesn't work because all your data are collected in your lab, and it's very hard to provide generability. And third is improve the model's experiences. So basically how to actually make the model to perform is very important. Like for example, folding napkin, you can fold it in 10 minutes. You can also fold it in 30 seconds, right? So if you deliver a model to your clients folding napkin, 10 minutes per napkin, then definitely your clients will say, okay, I don't want it, right? So that's very important to improve the model's like performance on that front. So here is a demo that we showcase we can already reach some level of that. So my co-founder Jason did another talk in another conference just 2 days ago, and we record a very interesting, so this is what he's talking on stage. So we literally just bring our robots onto the stage and showcase. That's zero shot. We didn't do any on-site data collection on this stage. And all this data, all this model are trained on the data that we collect in our office or with our partners. And we didn't do any specific tuning for this. We only set up for 20 minutes, and then this robot can just do. So this whole lecture is around 20 minutes. So if you look at the robot, it's just doing his job. continuously. It doesn't complain anything. So finally, we got around like 10-ish t-shirt gets folded pretty well. Yeah, so although like in the middle, you can see like the robots sometimes get struggled. It's trying to flatten the t-shirt. It's trying to like grab it more accurately. But finally, you can still figure out. It's just like sometimes it's taking a little bit longer. Yeah, so we are like internally within our team, everyone is very proud about this achievement because this is our first time that we actually do zero shot. Because previously when we want to deploy any clients, we still need to do some like on-site data collection, but this time it's purely zero shot, like everything worked out of the box. Yeah, and also if you look carefully about the lighting condition, like it's actually changing a little bit. I can see. Yeah, so for example, here the light gets darker, and then it gets back to like more warm and lighter lighting condition, but it doesn't affect the model at all. So the model just keeps on doing its stuff. Yeah, here's some other demo that we attended a conference for the hospitality industry, which is called Clean Show. So basically all these demos that we don't have anyone monitoring all these robots. They are just doing the job by themselves. And you can see all this audience, they are just looking at all these robots doing. So it's actually very interesting that like our employee in the company always like just sitting there watching what our robots are doing. So it's very interesting, and you can observe like very interesting behaviors it performs. Yeah. So here we demoed like t-shirt folding, clothes folding, and there should also be, yeah. So this one is for like clothes splishing. Some laundromat have this requirements. But again, we're not just about folding, because a lot of people feel like Dyna is a folding company. So yeah, we want to be clear, folding is just one of the use cases we want to tackle first, but we are not just about folding. Yeah, here are some latest demo. We haven't publicly released anything, but we are doing more diverse job than just folding. So this food chopping. So like before we actually start doing this task, we feel this is really hard because like how you actually hold the knife is very tricky. Like even for human, it's not that easy to like chop the celery in like very, in a very even way. But after some data collection and training, we really see this this very robust policy. And all you need is keep on feeding it the celery, and it will chop to the end. Like these days in our office, we have really huge basket of chopped celery every day, and I even take some back to my in-laws so they can cook for me. Yeah. And this one, yeah. So this one is to showcase how dexterous the policy can be. So basically this cup, it's very hard to actually grab the cup because right now we haven't started using tactile sensing or pressure sensor. So the robots need to be very precise on like how much force you need to apply onto the cup so that it can only grab one cup at a time. Otherwise, you will just grab the whole stack up. So we tried multiple times, but finally we get it work and work really pretty well. So for the precision and accuracy, and also we did like in total we did 5 times in a row. It doesn't fail. So it also really shows the robustness of our policy. Sorry. And this one is for preparing, like just for restaurant. We are helping them to preparing the utensil package. So it's a long horizon task because you need to, first of all, you need to fold the napkin. Second, you need to put all the forks and knives into the napkin. And third, you need to combine everything together onto a tray so that you can serve to the user. So yeah, so if you look at it, it does really good job. And like the whole task, even human doing that, it will take several minutes. And finally, our robot can do like similar things as that. Yeah. So the most impressive part is actually inserting all these knives and forks. Yeah, we can wait a little bit. Yeah, so this is a very impressive part. Yeah, sometimes even for human, this is hard. Yeah, and lastly is even longer horizon task. So we have some agentic reasoning. I'm not sure if you're familiar with this term, but basically it's a chain of thought about what needs to do next, so that it can, if you see it, grab the bread, put it into the grab machine, and then it start the coffee machine, and then it can do, like, it put some other stuff on the bowl, and then it wait. So this waiting part is actually very interesting, because right now for a lot of policies, you have to do something. Because how the robot runs is actually, it looked at the current scene, and then it decide what next things to do. And then if you look, sorry, if you look at the current scene, in this scene, if you only look at the snapshot, there are actually a lot of things you can imagine that you want to do, but the robot kind of memorize what it's already done, so that it just keep on waiting for the coffee to be ready, and then it prepare the breakfast and to the people. Yeah. We also have more agentic reasoning showcase. So the sound, yeah, I can only play with this sound, so it's not very clear. Yeah, so here just our engineers asking the robot for some candies, and it can accurately pick whatever you're asking. Yeah.
Can I get a Reese's and 2 Kit Kats, please?
If I gave a sixth kind of candy and told what it is,
Oh, sorry.
if I gave a sixth kind of candy and put it there and say what it is, would it be able now to start serving?
Yeah, so right now we only train on 5 types of candies. The 6 doesn't work, but I can show you a more robust thing that within these 5 in a bit. Yeah, so this is a more interesting one, which is we are not memorizing the position of the candies, but more it really recognize what candy it is. So even you shuffle the candy boxes, it will still pick the right candy. Yeah. But again, I mean, like, if you really want to add more candies with more and more data, more diverse data, as long as the model can finally recognize what candy it is, then it will be be able to pick it up. Yeah, right. Yeah, you're right. But we do have like 2 red candy, very similar. Yeah, but again, it's some challenging tasks we need to work on. Yeah. Okay, yeah, then I'll talk about the robustness part. So what I just showcased is more like how diverse what we can do, and also with the napkin folding thing, we showcase the zero-shot capability right now. But I also want to discuss a little bit about the robustness. So we released our Dyna 1 model several months ago. So if you're interested, you can get online to check it out. So first of all, let's study this napkin folding problem. Like I mentioned a little bit about how hard it is, but honestly, it's not a very simple job. So you see that right now it can fold very well, but if you really dig into the details, so here you see the challenging part is precise manipulation. You have to really just grab one napkin at a time. Otherwise, you are folding multiple napkins at the same time. And also from clients, there are very strict requirements on the final product, on the final result we deliver. So basically, our clients told us, hey, this needs to be with this length. it cannot be even longer than 1 centimeter. Otherwise, they can't actually insert their fork and knives into this napkin wrap. So internally, we kind of split the quality of the end product to like 5 grades. So grade 5 and grade 3 is only this difference. So for robot, it's very hard for it to differentiate if you don't do a lot of very accurate data collection. And then we can go back. So here is what we did for Dyna 1. So we literally get the, we get the robot run for continuous 24 hours, keep on like folding the napkin, and you can see that like this got speed up a lot, but you can see the clock here. It's actually a real clock because we want to showcase that it's not a staged demo. But basically, although like in the middle you can see the stack gets a little bit messy sometimes, but finally the robot can always recover by itself. You also see like the sun gets up, so it's very interesting. And we hit more than 99% of success rate. So basically, like among the 850 napkins, we only have a few that's like folded in a wrong way, or like finally it's not folded. And it's not just one time. We actually did it multiple times. Like you can see, this will shoot for like on different days. So we want to just make sure our policy can consistently do the same thing instead of like just we're lucky that we catch that one time. So these are the problems we discussed. But it wasn't that performant at day 1. So in day 1, it's like this. So barely can do anything. And finally, it gets stuck and almost kill itself. So this at the beginning. So I think like right now, there are a lot of research labs doing this type of research that claim that they can hit, for example, 80% of success rate, or like even a little bit higher. But if you think about like if you want to do this single task for 100 times, 80% wouldn't be enough at all, right? Because it means 80% like times 80% by 100 times, right? Then finally the number will be very close to 0. So if you really want to get it more robust, then your single success rate shouldn't be only 80%. So we internally built some infrastructure to help us to better collect like high quality data. So one thing we did is called a reward model. So basically when, like if you look at how it's folding the napkin, you can see our reward model can, based on the scene, it gives a reward about like where you are for the whole progress. So this is a very useful tool for us to actually select the correct data to actually be trained on. Otherwise, if you train the model with like bad data together with some good data, then the performance will definitely not hit the performance you want. And here is, we also have logical separation of different steps so that you see the robot is actually like doing things from step by step. So for most of the good data, you can see the curve for this reward model is actually very smooth. But there will be some accident. For example, for this one, it gets stuck. It just doesn't, like, it messed up with a napkin, and then it tries to like reorient all the stuff and then redo it again. So when we are doing data selection for the training, we can leverage this information to decide, okay, this kind of bad data for us, and then we'll only select the good data for the training. Yeah, this is also to showcase the error handling and robustness. So basically, you see it pulled out multiple napkins at a time, and then it tries to put back one by one so that finally it can just fold one napkin at a time. So this is important for clients because for all the clients, for example, for this restaurant, currently they have some people that's folding this, or even if you deploy the robot, they need to have someone to keep on monitoring the robot, because if you don't have this error recovery, then the robot can easily get into this situation and just get stuck there. So we kind of build this to make sure that when we deliver this robot to our clients, they don't have to pay much attention on that. They can just get it, keep it running, and then it will just deliver by itself. Yeah, so here it's also trying to like fix the folding a little bit. Yeah, there are a lot of like small tricks that you have to do actually to get the model perform well. Yeah, this is another example of error handling, like it poured in multiple napkins. Yeah, they even poured the whole stack and then put it back. So now you see like this stack is also pretty messy. Like it's not like a stack anymore, but again, it can still figure out, okay, here's the napkin and it pour over and then try to get it work. Okay, I will continue. Yeah. So as we mentioned, that we are a very deployment-focused company. So we have some real restaurant deployment already. So this is from real restaurant. Yeah, so basically right now for the restaurant staff, all they need to do is once this bin is full, they take out the bin and then put another stack there, and then the robot will keep on doing. So we have been serving several restaurants for a very long time already, yeah. Okay. Yes, then I will discuss a little bit about the open challenges. So although like I just showcased a lot of very interesting stuff, but again, it's still very far away from making everything general and possible. So there are several major challenges we are facing. One is model evaluation. So the reason that we can't get this performance because we run thousands of models every month. Right now it's all manually with some like data collector or some evaluator just sitting there watching what the robot is doing and then recording about this, like what the grade they actually performed. But finally, we definitely want to have some like easier loop that can do model evaluation. For example, in autonomous vehicles, they leverage simulation a lot to do that. But so far for dexterous manipulation area, simulation is still a very hard thing to actually accurately evaluate your model. So the model's performance is still like very dependent on the real data. And secondly is learning from low quality data, because as I showcased, there are a lot of data generated, but a lot of them are kind of low quality and cannot be directly used. But again, all these low quality data are kind of useful. It's like if you look at the large language model area, people are using low quality data for pre-training, or sometimes even for post-training, fine-tuning, or even for reinforcement learning, because the model can have some level of generability if your dominant data is still good quality. But right now, in the robotics space, so far, because the data scale is not there yet, so we haven't seen a lot of sign on that. But there are a lot of active research on this type of like how to leverage low quality data. Also, another type of low quality data is more on, like for example, the human video data, which is like just egocentric towards like human doing something. And finally, we also want to see if we can leverage that type of data, transfer the knowledge onto the robots, so that like then we open a really huge door on like getting more data. And third is about future improvement at deployment. So basically, right now, although we just finished one zero-shot demo in another conference, but again, for most of our clients, we still need to send a data collector and help them to collect some data on-site to adapt into the environment. This wouldn't be a very scalable business pattern, right? Because every time launching a new client, you still have to do that. So how to actually make this simpler is also another thing we are exploring. Like we are exploring different technologies to like help troubleshooting the device on site very easily, and also to reduce the number of data we need to collect on site for them. Yeah, and this is our team. So we are very close to this site. We're in Redwood City, 10 minutes drive. So if anyone is interested, very welcome to get onto our website or directly connect with me. And finally, I also want to showcase a very interesting thing we did with the robot. So we are not just a bunch of very strict engineer, but we are also like building fun stuff. Yeah, but I mean, it's not 100%. We just catch a very great moment. Yeah. All right, that's my talk. Thank you. I don't know. I'm asking. Do we have Q&A? Oh, okay. Sure. Go ahead. Okay, go ahead.
Okay, what do you think is most missing to make the next step here? Is it data or is it something else?
Yeah, data is definitely one very important piece. As you see, like right now, the data acquisition is very complicated. So we definitely want to make this much easier and more scalable in the future. Yeah. The power source? Yeah, so right now, most of the tasks are still stationary, so we have a power cable. But in the long term, we are also looking at like mobility type of thing. Then it will be battery. But it's an open question. I know a lot of companies are exploring different batteries, all this stuff. Yeah. Can we have more? Let's see. Yeah, go ahead.
Can you talk a little bit about how much you learned from demonstration, for example, the golf example? You learn from something from demonstration, and then some of it is in closed loop. How does that mix a little bit? Can you talk about that?
So your question is how much data I need for this demonstration?
Yeah, no, how fundamental is to see some demonstration data and some of it closed loop?
I see. Yeah, I think demonstration is definitely a way that you can teach the model to learn something new. But so far, we didn't see very scalable ways. Again, like you need to have very great foundation model first, and then your demonstration prompting can actually work. Yeah.
How much do you use simulations at all?
We have very small portion of simulation data, but right now it's not significant.
It's not helpful then.
I can't say that at the moment because right now we haven't spent a lot of effort to explore that, but some simulation data will be helpful, I think.
Really cool to see this kind of cutting of vegetables and restaurant napkins and stuff like that. Or looking at scenarios like maybe where today it's very hard for humans to do disaster recovery situations or situations where there may be human safety
Yeah.
involvement.
Yeah, we are definitely looking at that. Yeah, I think that's very great use case for robots. Definitely, we don't want to sacrifice human for those jobs. Yeah.
Can you talk a bit about catastrophic forgetting? So you have the PLAs running. How much of the information already in the base model do you actually preserve at the end, or do you end up completely rewriting that?
Yeah, so actually we see a very great trend, which is we are kind of getting rid of the post-training step more and more. Because originally when the foundation model is not that strong, like we need to do a lot of post-training for adapting to specific use cases. But as we feed more data into the pre-training model, then the pre-training model itself actually, like it can memorize a lot of information. So like these days, we only need to do probably like half day of data collection on site, then everything can work seamlessly. Yeah, so it's very, like the pre-trained model can memorize a lot, yeah.
So there are quite a few companies doing foundation model for manipulation, there's physical intelligence, others. What's maybe your angle, unique at Dyna?
Yeah.
What should we think of you? And
I mentioned a little bit at the front, which is like we focus on deployment and the research at the same time. I think that's kind of a very different angle. So if you look at some other companies that's A lot of them are very focused on the research part, or a lot of them are also very focused on the deployment part, like creating very customized solutions for their clients. We kind of want to combine them too, because finally we realize the robot policy needs to be general, otherwise your cost for expanding your business will be really high. Yeah, so that's kind of our unique role, yeah.
So are you training on different embodiment, and does that benefit you?
Yeah, so far we only train on our own hardware. We haven't seen very significant boosts from cross embodiment. We also tried out some open project like Google's like RTX, all this stuff, but didn't see like huge boost. It improved a little bit. So since we are focusing on deployment, so I think like single embodiment is good enough for us at the moment. Yeah. Yeah. Yeah, so like I mentioned at the beginning, like we leverage the research to tell us what type of applications we can actually choose at this moment. For example, like right now, we intentionally didn't choose a lot of tasks that requires mobility because so far we think like stationary manipulation is more like most reliable way to actually land. So the cycle is we do some, we unlock some capability of the model, and then we'll look for specific areas that this capability can help. So that's our philosophy, yeah.
So I saw the demo like 24 hours training, and maybe if you imagine like there are some case you totally messed up, is there any mechanism to recover from the good state?
Yeah. So I mean, one is definitely from some training data, so that like you also include some error recovery into the training data, so it knows how to do that. And secondly is, as you see, we have this like reward model, all this stuff, so the robot can actually identify some catastrophic scenarios and then reset itself. So we literally have a feature, if you get stuck in the middle for too long, then it will reset itself and then redo the task again. Yeah, so this can prevent the robot actually getting into a very messy state and just stay there. Yeah. All right. That's it? Okay, thank you.